To start today, I'd like you to try these 3 questions, so pause the video, give them a go. These questions essentially are testing you on your right angle trigonometry. Can you work out missing sides and angles? If you struggled with them, then I highly recommend that you go back and revise that because we're going to be pushing on today into more complicated aspects of trigonometry. In any case, let me go through them. So the answers are here. And let's just talk about what's going on. So when we do normal right angle trigonometry, we're using the idea of SOHCAHTOA, and that is 3 relationships between sides, essentially, the opposite and the hypotenuse, adjacent and the hypotenuse, and the opposite and the adjacent. What we have is that the opposite over the hypotenuse for a particular angle in a triangle that you're interested in, it will always be the same, and that's the thing that we call sine of the angle. It's all based on similar triangles. But just to go back to solving this, right, I've got an angle here. I've got a right angle here because the tree goes vertically up. So this is going to be the opposite, and this is going to be the adjacent, with this one being the hypotenuse. But I'm not interested in that one, so I'm going to leave it. I know the adjacent. I want the opposite, so it's going to be using this one, tan, and it's that tan of the angle is equal to the opposite over the adjacent. That SOHCAHTOA just gives you a little brief way of remembering that. So for us, it's going to be tan 33 equals the opposite, or the height, over 31. So the opposite is going to be 31 times tan 33. We normally write it that way around. You can write it as tan 33 times 31, but really you should put it in a bracket and then put a times in there. That's just good practice. So 31 tan 33, which gives us the 20.1 I talked about. If you go with tan 33 times 31, that won't give you the right answer because the whole thing's in the bracket. You'd have to close the bracket and then you get the same answer. For the angle, this time we've got an angle over here, so we've got the opposite and we've got the hypotenuse. Not interested in the adjacent. We're going to be using sine. This time it's going to be that sine x is the opposite over the hypotenuse. In our case, sine x is equal to 5 over 8. Now we're applying sine to x, and it's essentially a function. We only really talk about that briefly when we introduce trigonometry, but it is a function. It's doing something to x to give a number, so we have to do the opposite of it, and that is to do the inverse of sine and apply that to 5 over 8. And that should give us 39.7. So shift sine, and then 5 over 8, we can just do 5 divided by 8, which gives this 38.7. Brilliant. Okay, last question. The area of the triangle ABC is 50 centimeters squared. Find the value of sine F. What is the size of angle F? Okay, to deal with this, we need to think about, use the area of the triangle to start with. So it's going to be, for part A, that a half times the base, half times base times the height is going to equal 50. And then we need to solve that equation. You might have done it more intuitively. You might have thought, right, I've halved. If I have the base, I'm going to get 10. It's 10 times the height is 50, so h has to be 5. I'm doing it sort of a bit more slowly, but yeah, h is going to be 5. I'm just going to add that on there. That was the height. And now if I want sine of angle F, right, it's just sine F is the opposite over the hypotenuse. It's just 5 over 10, which is where that 0.5 came from. You could leave it as a fraction if you prefer, a half if you simplify it, or you could write it as a decimal. Now, what is the size of angle F? Well, in this case, we can just do F is inverse sine of 0.5, or you might actually know them, that is actually an angle that you're expected to know. Let's do it. Inverse sine of 0.5. You are expected to know that sine 30 is equal to 0.5, so this could, in theory, be a non-calculator question, but that's not something I'm going to focus on right now. The angle here is going to be 30 degrees. So I'm hoping you're happy with this. Trig with sides, rearranging, trig with finding angles, and then one that kind of mixes up a few other aspects. Today we're going to be looking at something called the sine rule, which can be used to calculate sides in any triangle. It's a relationship that's true for any triangle. And why do we need such a thing? Because SOHCAHTOA, which we've been using, only works for right angle triangles. We have a right angle as one of the angles that we know, and then maybe we know another angle and we know one other side, and that allows us to work out the other sides. But what if this wasn't 90 degrees? What if it was something else? It actually turns out that you can still do a similar sort of thing. There's a relationship that exists. Now I could tell you what this is, but I really want to, it's nice to sometimes just play with maths and see where it comes from. So bear with me, it's right under here, but I'm just going to kind of take this triangle and see what happens when I play around with it. I've labeled the triangle, the sides A, B, C with lowercase letters. That's quite standard. Especially we don't have a hypotenuse now. We're not going to be, we're not going to be labeling it. I'm not going to be labeling it opposite, adjacent, and hypotenuse. There will be one longest side, but the hypotenuse only refers to when you have a right angle triangle. I've then got angles A, B, C, and look, they are opposite the sides that with the same letter. So that is also very standard practice. There's nothing stopping me labeling the bottom one little a and the top one capital A, and then swap them around. So this will be little c and capital C, or whatever you like. There's nothing special about how I'm labeling it now. All right, let's do this. So what we're going to do, how are we going to get a relationship between these things? That seems very difficult. But we have something in our locker, and that is SOHCAHTOA for right angle triangles. So what happens if I put a line down from the angle that is at right angles to the base? There's nothing stopping me doing this. I've got a right angle here, and I've got a right angle here. And then, I don't know this length, but maybe I call it the height, so I'll call it h. Well, suddenly I can write down a relationship between the sides, because I could write down that sine of capital A, if I just look at this triangle in red, is equal to the opposite, which is h, divided by the hypotenuse, h over b. And that would allow me to write h as b sine A. Okay, like how does that help? Well, it doesn't at the moment, but it's maybe, I can write this down. How does it help actually? Because now I can look at this green triangle and I can do exactly the same thing, but it's going to be sine of B equals h is the opposite over A. A is now the hypotenuse of this green triangle. And then I can write that h is equal to A sine B. And this is fantastic because I've got that h is equal to b sine A, but it's also equal to A sine B. It's equal to both of them, and therefore I can basically get rid of h, I can eliminate it, and I can write down that b sine A equals A sine B. And if I want to, this is what we typically do, I could rearrange this. So I could divide through by sine A, and I could divide through by sine B to create A over sine A equals B over sine B. Now, what's happened to C? Well, it just so happened that because I split it in half this way, I kind of, C wasn't a very useful thing to use. I could, if I wanted to, split the triangle like so. So now there's a right angle up here. And And that would create another relationship. And actually, it would be a relationship in terms of which one would it be? It would be in terms of C and B. And what I'd find actually is that B over sine B is actually equal to little c over capital C. Or to finish this, the sine rule, which is actually this. There's nothing special about, just the way I split it meant I didn't get this relationship, but I can get that if I split it another way. And you might want to see if you can get that yourself. I'll leave that as a challenge. But this is the sine rule. Now, normally we don't need all six things. We will just label the triangle, and then maybe we would just use A, B, sine, capital A and capital B. But you'll see that in a minute. But this is the full thing. We've got it using right angle trigonometry. So I hope you're happy with that. We're ready to use this thing. So essentially, what's going on? We've now found a relationship between pairs of sides and angles. Okay, and it did exist before. Let's say that actually, if this was little a and this was capital A, and this was little b and this was capital B, in that case we would get that we'd get that A over sine 90 equals B over sine B. But actually sine 90 is just 1. That is also a value you're expected to know, but we could put it in our calculator for now. 1. And then this would go. And if you rearrange that, you'd have to rearrange it. I'm maybe going into more detail than I need to here, but sine of, sorry, that should be a capital. Sine of B is gonna, A sine B is gonna equal B, and sine B is then equal to B over A. And what I get is just the opposite over the hypotenuse that I used to get. B is the opposite, A is the hypotenuse. What I'm trying to say here is that the sine rule is just an extension of SOHCAHTOA, for sine that is. And if we put a 90-degree angle in, we will get back to SOHCAHTOA. Like it's a SOH, the SOH part of SOHCAHTOA is a special case of the sine rule. The sine rule is a more general formula that we can use. Right, we're going to have a look now at how we can use it. I should just add that this formula is not given in the formula book, so you do need to learn it. So make a note of it. The more you use it, the easier it will be, of course. And knowing when to apply it is something we're going to be looking at in more detail, because it's not the only technique that you might need. But recognizing you've got an angle pair and then being able to bring out this formula is a must. Let's see the sine rule in use. Calculate side y. We don't have a right angle here, so SOHCAHTOA is out the window. But what we do have is a newly found formula, the sine rule. How are we going to use it? Well, first things first, we need to label our triangle. We can label, let's just pick a smaller side to label, and why not go with this as little a? And then that one will be capital A, has to be. This is little b, and this one will be capital B. I could use C if I want to, but it's enough. I've got this part. I don't need all of it. This, I'll generally just be using just two parts, and I can choose how I label it. I'll just use A and B. Then I can write down the sine rule here, where I substitute in for A, which is y, and capital A. So it's going to be y over sine 105 equals b, which is 7, divided by sine 35. And I've created an equation for y that I can now solve. So a bit like when you have y divided by 2 equals 4, what we do is we times both sides by 2. Because if I got half of y, if I want all of y, I need to double it. And then I got all of y, and so y is going to equal 8. You might be able to spot that it was 8 by just thinking, what do I divide by 2 to get 4? But the kind of way of doing it with equations, the balancing method, is to times through by 2. And sine 105 is just a number. It's a bit like 2. So we can literally times through by sine 105. That will get rid of it from the bottom. And we'll be left with y equals, now, when I times through by sine 105, I just times the top by sine 105. So it becomes 7 sine 105 all over sine 35. If you want a bit more on why we would do that, well, you can imagine timesing by sine 105 over 1. You times the tops with fractions, you times the bottoms, we're going to get the same thing. And we're basically done. We just need to now put this into our calculator. So I'm going to use the fraction button, 7 sine 105 divided by sine 35. 11.788. Which I'm going to round to 3 significant figures, 11.8 centimeters. And we've managed to calculate the side of a triangle where we don't have a right angle. We just happen to have these angles, well, an angle side pair and then the angle that's opposite the y. Little question, how could we calculate the other missing side? I want you to pause the video, see if you can do this. Right, the other missing side, I'm now going to need to label, so it's going to be little c, and this is going to be capital C. What can I do to sort that out? Well, I actually know A and A now, and B and B, so I can use either one of those with C over sine C. The only thing is, do I know what capital C is? Well, I do, because actually I've got a triangle that adds to 180. 35 plus 105 is 140, so it must be that this angle is 40. So sometimes you might be asked to I could have been asked to calculate this straight off, and it's okay. Instead of being asked to find y, I might have been asked to find this one, and I just have to realize to work out the missing angle. So it's going to be c over sine 40 equals, and now I'm going to use the b over sine b, because just in case I made a mistake with y, or I've had to round it, so I'd have to use the full thing, I might as well use b because it's much simpler. So 7 over sine 35. And now it's the same thing. I times through by sine 45, so c is equal to 7 sine 40 all over sine 35. .844, which may be around to 7.84 centimeters. So a really good question that applies and needs the sine rule, and we can actually find both sides. Really powerful method. I want you to have a go at this one. So I've gone for an example, and I've even shown you how you can work out a missing side when you don't have one of the angles. If you know two angles, you can work out the other one. Give this one a go. Can you calculate x? And then actually my little extension, which I haven't got the answer for at the moment, is to calculate the other missing side. And essentially then you have all the angles and all the sides. Go for it. Right, first things first, they've labelled a triangle A, B and C, but I don't have to use that. I could change it if I wanted to. I could make that C. In this case, probably best to just stick with it. So this is going to be little a, this is going to be little c, and little b. I'm going to be using the sine rule. It's going to be x over sine 48, because that's the opposite angle. I'm doing this a bit quicker now. Actually, let me just show you the answer in case you've done it and you're like, I just want to check my answer. 12.7 centimeters for x. So x over sine 48 is going to equal, and now so I'm using that one, and now I can just see that I can use this pair, and it's going to be 16 over sine 70. If you want a little bit more scaffolding than what I've used is b over sine b equals little c over sine capital C. Yeah, I just jumped straight in and applied it, but that's what's going on. And I've not used A because I don't know what capital A is, and I'm sorry, little a is. I'm not interested in that. And I could work out what capital A is. We'll do that in a bit. That means x is going to be 16 sine 48 all over sine 70. And that should give the 12.7. 12.6, always good to write that out before you round it. 12.653 equals 12.7. Okay, I challenge you to do the other missing side. How'd you get on? First of all, we're going to need to add these two angles up. That's going to give me 118. So it should be 162, but let's just check. I don't want to rush it and make a mistake. 48 plus 70 is 118. 180 minus that, 62 degrees is going to be this angle here. And now I can use that A over sine 62 is equal to 16 over sine 70. I've just used A over sine capital A is equal to, and then again I used I used C over sine capital C. That's what that is. So let me get rid of that so it doesn't look too confusing. The A is going to be 16 sine 62 over sine 70. .03 or 15.0 centimeters. Well done if you got that. Well done for your efforts on this. That's the main bit of the lesson. We've spent some time deriving the formula. It's got to be said. Oh, up here. Okay, really, really good idea is to try and make sure you can do that yourselves. Great if you can. It's a proof of the sine rule essentially. Examples, other missing sides, same again. Hopefully you had a good go at this. Now it's just a case of doing a bit more practice. And here is some more practice of using the sine rules. So we've got these different situations, very similar to the examples I've gone with. And you'll see, yeah, in pretty much all the cases the angle's given, but get through those, it's really good. And then here are some extensions with bearings in, but actually the diagrams are there. I just want to say, if you haven't covered bearings or it's been a while, the bearing is the angle from a north line that goes clockwise to the line that you're interested in. So for 10, you're going to have to draw your own bearing. So the bearing of y from x is 205. So that will tell you, right, if you're at x, then and you put a north line in, then you're gonna need to do an angle that goes around 205. So 180 is down, so it's gonna be a bit like that. And we're only doing sketches, but it helps to make it roughly accurate. So then it's gonna be here. And then you can do z from y is 315. I'll let you think about that, but yeah, that's bearings. Bit more going on because you've got these angles on the outside, so you're gonna have to think about how you're gonna have to think about bearings a bit. I'll talk about that in a second actually. But these are the questions, here are the answers, check them, make sure you're happy with them, really important. If you are stuck, then here's, especially on the bearings ones, then the little hint really is that you've got to realize that actually you've got co-interior angles going on. So if this was 40, then this angle is 140 because I have to add to 180. The reason being that this is a corresponding angle. These two are corresponding angles, so that is 40, and therefore these two add to 180, and therefore these two add to 180. Well done your efforts. Keep going with this. We're going to be looking at the next. What we haven't done today is look at how to calculate angles in non-right-angled triangles. So that's coming up. Looking forward to it. The other thing that's not going to be quite yet is, well, what happens when you don't have an angle pair at all? And that is going to involve another little bit of math. So there is more to do on non-right-angled triangle, but good start.